Hello and welcome back here to chapter 7. This is part 2 of our lecture series here on chapter 7. Before we learned about grams and moles in this chapter. Oh, a little stretchy, hang on a second here. Let me fix myself. That better. In this part we'll learn about percent composition by mass and two important formulas, the empirical formula and the molecular formula. And now, part 2. Okay, welcome back here. We're doing chapter 7, part 2 right now. So last time we talked about really the basis of a lot of the calculations we're going to talk about here for the remainder of chapter 7. We talked about our molar mass, which is our grams per mole. Remember, that is the conversion factor that you could get from the periodic table. It is the number that you see below the symbols, and that is how many grams there are per mole. If it's just one element by itself, you just take the number off the periodic table, the four significant figures. Again, if it is a compound that has multiple elements in the formula, you basically just add up all the parts like we did with water. You take 2 times 1.008 for the hydrogens, and you would add 16 to it for the oxygens, giving a molar mass of 18.02 grams per mole. Remember that the number always stays with the grams part, and it's always per 1 mole. The other important thing we talked about in terms of molar mass was the idea that it is always done based on just the actual chemical formula by itself. So if you ever need to calculate the molar mass, you want to make sure you just take the formula, go to the periodic table, and add up all the parts. The molar mass, which we do get from the periodic table, again, is our conversion factor. You need to go from grams to moles or moles back to grams. That is your conversion factor, and that is something that we use a lot in chemistry. So you definitely will see that pop up in multiple places throughout this semester. Your continuous journey through chemistry, you'll see it a lot. So it's definitely something you want to always make sure you master. We also talked about Avogadro's number. Remember that Avogadro's number is 6.022 times 10 to the 23. The units of Avogadro's number can be atoms, they could be molecules, they really could be any unit you want. Most of the time here, though, in chemistry, we're looking at atoms and molecules, and that equals 1 mole of something. So the idea of a mole is the same idea as we talked about of like a dozen means 12. A pair means 2. A mole means 6.022 times 10 to the 23. And again, that's Avogadro's number. That is basically also used really as a conversion factor. And that is a conversion factor between basically moles to atoms, or molecules, or backwards molecules back to our atoms back to moles. So remember that we don't want to overuse, if you will, Avogadro's number. You want to make sure that you only really use it if there's some mention of atoms or molecules, or there's some mention of atoms or molecules that you need to solve for. So either you're given a number in atoms or molecules, or you're asked to solve for a number in atoms or molecules. Remember, if you're not given pretty much any of those things, you should just leave Avogadro's number sort of to the side and not use it. We also finished up talking about sort of a variation on some of these calculations that we were doing, where we could actually use the formula itself for a particular compound as a conversion factor, where the subscripts that we see in those formulas represent the moles of each of them. And the way that we used them was a situation where maybe we were interested in how many moles of hydrogen or moles of carbon or atoms of carbon or atoms of nitrogen, whatever it may be, was in a particular sort of compound. So by using the formula itself, we were able to figure out how many moles of, say, nitrogen there was to 1 mole of the entire thing. So we're able to kind of relate the whole thing to the individual elements that are present. So that's also kind of a variation. You don't have to do that a lot, but sometimes you are interested in, an individual element rather than the whole thing itself. So works the same way, except you need to use that formula as a conversion factor. So these calculations that we talked about, specifically really the grams to moles, moles to grams, using the molar mass from the periodic table, is really going to come into play here with what's left of this chapter, which is talking about molecular formulas and empirical formulas. So molecular formulas and empirical formulas are two different types of formulas, and we're going to talk about how to calculate each of them. And we will use, obviously, some of that molar mass, grams, moles, and grams. So let's get into it. Let's talk about the molecular formula. A molecule, as we talked about, is really that basic definition of at least two atoms that are held together. Remember that a molecule is sort of a basic definition of, it could be two atoms of the same element. It could be two atoms or more of different elements. But your basic sort of definition of a molecule is you just need those at least two atoms to be involved. A chemical formula expresses what is present in a compound, and we use the symbols to represent how many atoms that are involved for each of the elements that are present. So a molecular formula is a formula that shows you exactly the number of atoms of each element that are present in a molecule. So when we look at the molecular formula, it tells us exactly what's there in terms of the elements and how many of each of those elements are present. And that is the molecular formula. We've seen the simplest type of molecules, which are diatomic molecules. And these are our formulas here, for example, for some of these diatomic molecules, like H2. Remember, again, as we've talked about, that subscript tells us how many of each of those are present atoms, and it always goes to the guy to the left. Now, molecular formulas can be written several different ways. And what I mean by that is a lot of times chemical formulas or molecular formulas, for example, are written in a very simple sort of form. They kind of just tell you what elements are present. So, for example, we saw this guy previously. That is ethanol, which is C2H6NO. And once again, that means, as we saw, there are two atoms of carbon. Also, as we saw, that represents that there's 2 moles of carbon in that particular compound. There's 6 atoms of hydrogen, or 6 moles. And again, much like in chemistry, when we have one of something, we don't write anything there. So it is not 0, just to remind you, it is 1. So that is 1 atom of oxygen. Now, this particular molecular formula here, our chemical formula, for example, doesn't give us a lot of information about perhaps how this compound is connected. Some people may also write ethanol in this form, CH3, CH2, and OH. Now, these are actually the exact same thing. Here, if we count up what we got going on, that's 1 carbon, 2 carbons, check. That's 3 hydrogens, 5 hydrogens, and 1 more makes 6. And that is 1 oxygen. So these are 2 different ways to represent the formula for a particular compound. And the difference here is the first way does tell you exactly what's present, just like the second way tells you exactly what is present. But the first way really doesn't give you information about the structure. And sometimes when people write molecular formulas or formulas in general, they'll kind of include a little bit of structural information. And that is actually what we see here. So if you were to draw ethanol, which probably a little later on, you'll know how to properly do that. It will look something like this. A little bit of that there. And a little bit. So this is what ethanol looks like when you actually draw it out, what is referred to as this Lewis structure. And if we sort of compare that to our second formula as it was written, CH3, CH2, and OH, we could kind of see what we're looking at here in terms of why it's written like that. So we have a CH3, that's 1 carbon and 3 hydrogens, which are right there. We also see CH2 next, and that's a carbon and 1 hydrogen and 2 hydrogens, which is CH2. And lastly, we see here, find maybe a color here. Yeah, I'll try that one. Hope for the best. I'll just kind of circle it maybe. We have an OH, and that is our OH here. So the second form, as you can see here, definitely gives us a lot more information about how this guy is sort of connected. And sometimes formulas will do that. And sometimes they won't. They'll just be basically, this is what is present. Another example of that is CH3, COOH, or sometimes this is written as C2H4O2. These are both what are referred to as acetic acid. And acetic acid is basically the major component of vinegar. And much like the ethanol example, this one pretty much just tells you what's present. And again, there's 2 carbons, 1 and 2. There are 4 hydrogens, 3 and 1 is 4. And there's 2 oxygens in this case. Now, this particular formula, the way it's written, gives you a lot more information about how it's connected. So if you were to draw acetic acid, it will look something like this. And I'll give it the old college try here. A little bit of drawing here. A little bit of carbon. So now if we look at sort of what is going on, again, it really does give us some of that information about how it's connected. Once again, here we see a CH3, which matches our CH3. We see a COH and O, which is basically what this is, COOH. And again, it gives us a lot more structural information. So it's very common. Sometimes in lab, it's also very, very common. Sometimes people will put labels on reagents that you use, and they'll just kind of use the basic formula of like C2H6O. And then sometimes people are used to it, seeing it in another way, and they think it's different things. So basic chemical formulas or molecular formulas here just kind of tells you exactly what's present. Sometimes they're referred to as sort of structural formulas, where you got a little bit more of the structural information as you see here. But they do both represent basically what is present in that particular compound. Now, different than a molecular formula, which tells you exactly what is present in a particular compound, another type of formula is what's referred to as the empirical formula. And the empirical formula is basically the simplest whole number ratio of what is present. So it may not necessarily be, as it says there, the actual number of atoms in a particular molecule, but it is the simplest whole number ratio of those elements present. So if we look at an example here that we have on the page, which is hydrogen peroxide, H2O2, the relationship here is for every 2 hydrogens that we have, we also have 2 oxygens. And that is basically a 2-to-2 ratio of what is present. And a 2-to-2 ratio is, if you just divide everybody by 2, is the same as a 1-to-1 ratio. So you could basically reduce everybody down and still have whole numbers. And that will give you HO, as you see there. And this would be the empirical formula for this molecular formula that is present here. And it is the simplest whole number ratio that's present. So an empirical formula will tell you, not necessarily in all cases, how many atoms are present in a particular molecule, but it will tell you the simplest ratio of who is present. So for example, if I had a C4H8, that is basically 4 carbons for every 8 hydrogens. That is basically a 4-to-8 ratio, which again, if you divide by 4, it's a 1-to-2 ratio, which means CH2 would be our empirical formula here. So if you could reduce down a formula and still get whole numbers, that would then turn it into its empirical formula. Now, there are certain formulas, as we will see, where if you had, say, something like H2O, for example, which is water, that is 2 hydrogens for every 1 oxygen that's present. Not really a 10, but a 1 oxygen there. And that's basically a 2-to-1 ratio. That is as low as you can go. There is no way to reduce that down any further. So there are certain compounds where both the molecular formula and the empirical formula are the same, because frankly, you can't go any lower or reduce them down any lower and still get basically a whole number. So you can't have a like decimal number down here in any of these things. They have to be whole numbers. So you can't have like half an atom present or anything like that. Now, all ionic compounds, and we've talked about ionic compounds, and the idea of ionic compounds is a positive and negative ion coming together. And when we put those guys together, we put them together in the simplest way to get to a 0 charge. And that means that all ionic compounds are empirical formulas, because the basic way that we put ions together is to equal a 0 charge, and the simplest way to get to a 0 charge. So always when you look at an ionic compound and its formula, it is always the empirical formula, because it should always be the simplest way to put those ions together to equal 0. Molecular compounds are a little bit different, but ionic compounds should always be really the empirical formula. So here's an example here of another one, N2H4, which is hydrazine. So when we look at this guy, once again, looking at our 2 elements, we have 2 nitrogens for every 4 hydrogens. And once again, that is a 2-to-4 relationship. And if you divide by the smallest number, that gets you a 1-to-2 relationship, both whole numbers, which means our empirical formula, as we see there, would be our NH2 for our molecular formula of N2H4. So remember, though, that only the molecular formula will actually tell us the exact number of atoms that are present. The empirical formula, again, is the simplest whole number ratio of what is present. So they do need to be whole numbers. That's a really important thing to remember as you are figuring out empirical formulas. Now, as I said before, there are certain molecules where both the empirical formula and the molecular formula are the same. So there's our water, NH3 as well is another example of that. Again, here, NH3 is basically 1 nitrogen for every 3 hydrogens. That's a 1-to-3 relationship. You really can't reduce it down any further. Same thing with carbon dioxide, which is our CO2. That's 1 carbon for every 2 oxygens. Once again, a 1-to-2 relationship, and that is as low as you could go. And obviously, we talked about our water a second ago being a 2-to-1 relationship. Here's a table from your book of some empirical formulas and molecular formulas. And again, we just basically reduce these guys down by dividing by the smallest number and still getting whole numbers in this particular case. All right, so why don't you take a couple of minutes here, and for each of these molecular formulas, why don't you figure out what the empirical formula is? Okay, let's take a look. So once again, this taking the molecular formula, we basically have 2 carbons for every 2 hydrogens. That once again is a 2-to-2 relationship, which means if we divide everybody by the smallest number, that is a 1-to-1 relationship, which means our empirical formula here would be CH. Looking at diiodine pentoxide, that is 2 iodines for every 5 oxygen. That is a 2-to-5 relationship. That means if I try to divide by 2, that's a little problematic. That's not going to give me a whole number here. That's going to be like 2.5. So that is no good. So that means that is really the simplest we could get it. So the I2O5 is both the molecular formula and the empirical formula, as that is the simplest ratio that is present. Lastly, here we have glucose, which is 6 carbons for every 12 hydrogens for every 6 oxygens. So that's basically a 6-to-12-to-6 relationship, Once again, here we can divide by the smallest number. And in this case, that's going to give me a 1. That will give me a 2. And that will give me a 1, which is this all whole numbers, which means our empirical formula here would be CH2O. So if you do have the molecular formula given to you, you could very simply figure out the empirical formula by dividing the subscripts, the smallest subscripts all the way across. And again, that should give you hopefully whole numbers. If it doesn't, like the case in the middle there, then you have already the empirical formula as well, because you cannot reduce it down any further. So again, no decimals on the subscripts. So let's talk a little bit about percent composition of mass. The formula tells us the composition of a compound, and the percent composition by mass is the percent by mass of each element that's present in a compound divided by the mass of the total compound and times it by 100. So basically, to figure out the percent composition of a element, you basically take the mass of that element, you divide it by the mass of the compound, then you times it by 100%. Now, clearly, if you have all the elements present, you should equal 100% when it's over, or pretty close to 100%. But that's how you figure out your percent composition by mass. So, for example, here, if we have hydrogen peroxide and we wanted to figure out the percentage by mass of hydrogen and the percentage by mass of oxygen, we would first want to start with the molar mass here of our hydrogen peroxide. So once again, we would go to our periodic table like we did previously in this chapter. Hydrogen 1.008, oxygen 16 on the periodic table. Big periodic table square there. There we go. So figuring that out, that's going to give us for H2O2, we got 2 hydrogens, each at 1.008 grams per mole. We have 2 oxygens, each at 16 grams per mole. And grab the handy dandy calculator here. 2 times 1.008 plus 2 times the 16. Going to give us 3402, we'll call it. Again, going about 4 significant figures here in the molar mass. And that is the molar mass of the entire compound. So to figure out the percentage of hydrogen, we would take the mass of hydrogen in this compound, which is 2 times 1.008 grams per mole. We would then divide it by the mass of the entire compound, 3402, and times it by 100%. So if we do that, we get 2 times 1.008 divided by 3402, times it by 100 here. And we end up with 5.926% hydrogen. So this guy is 5.26% hydrogen. Let me just fix that so it looks like maybe a better 5. There we go. We could do the exact same calculation for our oxygen. There are 2 times 16 for our oxygen that's present in this compound. We're going to divide it by the molar mass of the entire thing, which is 3402 grams per mole. And times it by 100% there. And that will give us 2 times 16 divided by 34.02 times it by 100. Going to give us 9406 here. Percent oxygen. So this compound by mass is made up basically of 94% oxygen and about just under 6% there of hydrogen. Now, remember that, it is math and it is percentages, which means I know I have 100% of all the elements present, which is hydrogen and oxygen. So I could, if I wanted to, actually skip the second part of this calculation and take 100% minus my first percentage there. And that should get me to the oxygen, since hydrogen and oxygen are the only elements that are present. So that's an alternative that you could have done there to figure out the percentage of the other element that was there, since it was only really 2 elements in this case. And you could do that in certain situations If you know, pretty much all the elements but one, you could add them together and subtract from 100, and that'll give you basically the missing percentage. You do get a slightly different answer with rounding, maybe like 9407, but pretty much the same answer as well. So let's take a look at the empirical formula here. What happens if we wanted to figure out the percent composition of hydrogen and oxygen in the empirical formula for hydrogen peroxide? So why don't you take a moment and figure out the percentage of oxygen and the percentage of hydrogen in this empirical formula here. I erase my scribbles off the screen. There we go. All right, so take a moment there and see what you come up with. All right, so let's see. Is it different or is it the same as what we just saw? I'm hoping you're saying to your screen it's the same, and maybe it is. So let's take a look and see if it is. So we will do the same approach. We're going to get the molar mass here of HO, which is our empirical formula. So that is 1 hydrogen at 1.008 grams per mole, plus our 1 oxygen, which is 16 grams per mole here. And that gives us a molar mass for our empirical formula of 1.008 plus 16, 1701, we'll call it. So we'll do our same calculation here. The percentage of hydrogen, going to be the mass of hydrogen in our empirical formula, which is only one of them. So that is 1.008 divided by 1701. And we'll times it by 100%. And 1.008 divided by 1701 times 100%. Going to give us, looks like 5.926% hydrogen. By the way, I'm going with about 4 significant figures on both of them based on the molar mass. Our percentage of oxygen in this case would be 16 grams per mole divided by 17.01 grams per mole times our 100%. And that is going to get us 16 divided by 17.01 times 100%, 9406. And dare I say, I think we hit the exact same percentages as we saw there for our molecular formula. So this illustrates the point that our molecular formula and our empirical formula are related to each other. They basically have the same ratio of elements that are present. And because they have the same ratio of elements that are present, they will also have the same percent composition of elements that are present. So both the molecular formula and its empirical formula will have the same percent composition of the elements that are present because they're really the simplest ratios of each other going from molecular formula to empirical formula. So let's take a look here. There we go. Here's an example from your book of that exact sort of relationship. These are all basically a one-to-one relationship between carbon and hydrogen. This is definitely a 1 carbon to 1 hydrogen relationship. This is a 2 carbon to 2 hydrogen relationship, which if you reduce it down is also a 1 carbon to 1 hydrogen relationship. This is a 6 carbon. I guess I said that backwards there. 6 carbon to 6 hydrogen relationship. Once again, if you divide by 6, that is a 1 carbon to 1 hydrogen relationship. They all have the same percent composition of these elements, even though they have different sort of formulas, but because they're related to each other by kind of the same ratio of each of those elements, we have the same composition of each of those elements that are present. So why don't you take a moment here and do a little calculation of the percent composition of each of the elements here in phosphoric acid. Let me give you some numbers which might be helpful in case you don't have your periodic table with you. Hydrogen 1.008. We have our friend phosphorus, which is 3097, I believe. So that is phosphorus here, which is 3097. And lastly, oxygen, which is 16. All right. So take a moment here For each of these elements that are present in phosphoric acid, figure out its percent composition by mass. All right, so we basically are looking for percent of hydrogen, percent of phosphorus, and our percent of oxygen. Once again, here to do this, we got to start with the molar mass from the periodic table. So we're going to add up all the parts. That is 3 times our hydrogen of 1.008 grams per mole. That then is adding 1 phosphorus at 3097 grams per mole. Again, coming from our molar mass from the periodic table. And we're going to add that to 4 times 16 here grams per mole, which is our molar mass there of our oxygen. Taking all those guys together, we're going to get 3 times 1.008 plus 3097 plus 4 times 16. That's looking like a 97.99 grams per mole. So now that we have the molar mass of the entire compound, we just need to take each element and do the percent calculation. So starting with hydrogen here, our percent hydrogen, there are 3 of them, so about 3 grams or so. 3 times 1.008 grams per mole divided by the molar mass of the entire compound. And again, we're going to times it by 100%. And if we do that, 3 times 1.008 divided by 97.99 times 100, not 1,000. Get rid of the extra 0 there. And that's going to give us, looks like 3.086% hydrogen. We're going to do the same thing for our phosphorus. So percent of phosphorus, there's only 1 of them, so that's 3097 divided by the molar mass of the entire compound. And we're going to times it by 100%. That's going to give us 30.97 divided by 97.99 times 100%. Going to go 3161. Sounds like a good number. 31.61% phosphorus. Lastly, here we could do it for oxygen. Percent of oxygen going to be, there's actually 4 in this case. 4 times 16 grams per mole divided by 97.99 and times 100% gives us 4 times 16 divided by 97.99 and times it by 100%. Gonna get us 65.31% oxygen. Now, again, in this situation, if you did not want to do the last sort of calculation here, because oxygen was the only element that was left, you could have added these guys together and then took 100% minus what you got here when you added them together, and you'll pretty much get that number right there. So basically, if you took 100%, you subtracted 3.086%, which was the amount of hydrogen, subtracted 31.61%, which was the amount of phosphorus. You pretty much get that. Once again, the last number might be a little bit off because of rounding, but that's, again, another way you could get that last sort of element that's missing. So percent composition is really just the percentage by mass of each of the elements present in a particular compound. It's used a lot with just figuring out the percentages that are present, but also with calculating empirical formulas that we're going to talk about here in just a second. We get that kind of numbers very commonly. And then we can kind of figure out the percentage a lot of times in the laboratory of different elements that are present. So it does come about a lot. All right, here. So let's speak about how we can actually calculate empirical formulas. We'll also talk about how to calculate molecular formulas. So earlier we were given sort of molecular formulas, and we could calculate the empirical formulas pretty simply by just reducing it down by dividing by the smallest number. Now, there's certain times where you might have to actually calculate the empirical formula using some data that's given to you. And there's several steps that you want to follow. So let's talk about really the steps to calculate an empirical formula. So the first thing you want to do is convert to moles. I'm sorry, convert to grams first. We'll get to moles in a second. And what I mean by that is you're oftentimes given the percent composition by mass of the elements. So what we were just calculating a second ago, you're very oftentimes in these type of problems told it's like it's made up of 32% carbon, 50% hydrogen, whatever it may be there, 20% oxygen. So what's an easy way to convert a percentage into a number? It's something that you probably do without thinking about it, which is assume 100 grams. When we assume 100 grams, that means that basically our percentages are going to be the exact same numbers as our grams. So you can think of it like you got 80% on your exam out of 100 points. That means you probably got 80 points out of 100. You got 90% on the exam, you got 90 points out of 100. If you have 30% carbon, that means you have 30 grams out of 100. So a very easy way to convert sort of percentages, especially percent composition by mass, into usable units is to assume that you have 100 of it. You could really assume as much as you want, but if you assume 100 grams of it, that keeps the numbers the same. So numbers don't change. So that's probably the easiest approach that you want to do. So once you have it in grams, I jumped the gun a second ago. Now we're going to take our grams and convert them to moles. So how do we convert grams to moles? Well, the first half of this lecture, the previous recording, we did nothing but that a lot of times. We're going to use our molar mass. Remember our molar mass from the periodic table, which is, again, our number on the bottom here, is how we convert everybody from grams to moles. Now that we have everybody in moles, the next thing we're going to do is divide by the smallest number of moles. So what does that mean? So I'm just going to do a really basic sort of example here to illustrate what we're talking about. So let's say we did step number 2 here. And let's say we had a compound that was made up of A and B. And after step number 2, we calculated that we had 4 moles of A, and we converted it in, we had 2 moles of B. So that would be obviously after we take the grams and convert them to moles. Now, the third step is we're going to take the smallest number of moles, which in this case is 2, and we're going to divide everybody by the smallest number of moles. We're going to divide that by 2. We're going to divide that by 2. Obviously, when we divide this guy by 2, we get a 1. We divide this guy by 2, we get an actual 2. If you do that like we just did right there, and you get all whole numbers, like we just did there in that example, that is going to be your empirical formula. So in our example here, our empirical formula would be A2 and B. So that 2 is how many moles basically, right? So that's 2 moles of A, and nothing written there means 1 mole of B. So this would be our empirical formula in this particular case. Now, if you divide and you get whole numbers, you're good. If you divide and you get pretty darn close to whole numbers, like you get like a 99 at the end, or like a 0.01 or 0.02, just slightly over the whole number, just slightly under the whole number, you could pretty much round to the whole number. But it's not always going to be that way. So let's say another example. Let's say we did number 2 here, and we ended up with 5 moles of A and 2 moles of B in this case. So what we're going to do in this case is the same thing. We're going to divide everybody by the smallest number of moles. And in this case, it is still 2. So we're going to divide everybody here by 2 moles. And now when we do that, we get a 1 for B when these guys cancel. But now over here, we get a 2.5 for A. And that would give us an empirical form of A 2.5B. The problem with this is that is definitely not a whole number. So as we've been talking about, it does need to be a whole number. That is not a whole number, so that's not good. That is also too far to round. So when you're calculating empirical formulas, it's got to be pretty much on that whole number for you to round, just slightly above, slightly less. If it is like 0.5 like this, other common sort of endings, 0.33, 0.25, these are too far to round. So what do we have to do in this case? We can't leave this because this is not good for our empirical formula. So we need to figure out a number to multiply this 2.5 in this example by to get a whole number. So you could just do like a trial by error. 2.5 times 1 is 2.5. 2.5 times 2 is 5. That's a winner. So what we need to do is actually multiply not by 5, but by the factor, which is a 2, to that number and also this guy. So not just the one that's not a whole number. We actually just multiply both of them by that factor. That would give us the proper empirical form A5, B2. And that would be our proper empirical formula. Happy face down. Because that is a whole number. So again, if you end up dividing by the smallest number of moles and you hit all whole numbers, you're good to go. That's your empirical formula. Box it up and move on. If you divide and you really don't get a whole number, so very common endings, 0.5, 0.33, something like that, too far away to round. You need to find that factor to multiply everybody by to get to a whole number. Let's take a look at it. Here's a table from your book of some common, again, endings that are really too far to round. You do need to find that factor. So again, 0.25 comes from 1 over 4. So really, if you multiply by 4, you'll get a whole number. 0.33, if you multiply by 3, gives you like 0.99, which is close enough to round. You take 0.5, multiply by 2, which is 1/2. 2/3 is 6/6, multiplied by 3, and so forth. So you can oftentimes multiply by the denominator, and you'll kind of get what you need. I would say probably in most cases, all these are possible, but probably these are going to be fairly common ones, maybe even this guy that you might come across. But again, these are too far to round. So too far to round. You need that common number to multiply by. Feeling that might be in my picture, so hopefully you can see what we're looking at here, but it's basically something like this, like 1 over 4, that's a common ending, 0.33, 1 over 3, 0.5, which is 1 over 2. So again, these guys too far to round, need that common number. But if you end up with a number like 1.998, and that's pretty close to 2, you end up with like 2.02, and that's also pretty close to 2. So if it's pretty close to the whole number, just over the whole number, you could round pretty safely. Otherwise, if you got something like this happening, you do need to find that common number. All right, so let's take a look here at this one. So why don't you give this a go and see what you end up with. We got vitamin C is composed of carbon. That's 40.92%. Hydrogen, that's 4.58%. And oxygen is 54.5%. Again, let me give you some numbers here that we've been using, which will help. Carbon, 12.01. Hydrogen, 1.008. Oxygen, 16. All right, so take a moment, figure out the empirical formula. Again, follow the steps. Convert to grams, grams to moles, and divide by smallest. Moles. All right, so see what you come up with, and we'll take a look at it here in just a second. All right, so let's take a look. So in this case here, we have basically 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen. So when you have all these percentages given to you, really one of the first things you should really take a peek at is, do my percentages add up to 1%? So if we just kind of quickly look at that, that's 40 and 54. It's approximately 55, and another 5 is 100%. It may not be 100% perfectly on the nose, but should be pretty close. The reason we do want to check this is if we are not adding up to 100%, we're probably missing a particular element here. So we would have to figure out what is the percentage of the missing element. You can do that by subtracting by 100. So since we are pretty close to 100 here, we could assume 100 grams. So what that's going to do is basically just turn all these percentages into the same number of grams. So that would tell us we have 40.92 grams of carbon. We got 4.58 grams of hydrogen, and we got 54.50 grams of oxygen. Next thing we want to do, we convert it to grams. We want to convert to moles. Molar mass is going to allow us to do that from the periodic table. So we will use our periodic table's molar mass. Obviously, if it's not provided for you, you got to go hit that periodic table to find it. They're going to take 12.01 grams per mole for carbon. We're going to divide by 1.008 grams per mole for hydrogen. Remember, grams on the bottom here, so they cancel. And 16 grams per mole for oxygen. So that is going to convert everybody into moles, which is what we're looking for. So we'll take our 40.92 divided by 12.01. That's going to give us 3.4072 moles of carbon. We'll take our 4.58 divided by 1.008. Going to give us 4.544 moles of hydrogen. And lastly, 54.50 divided by 16, going to give us 3.406 moles of oxygen. So we go one more. We'll put a 3 there, I guess. Now what we want to do is divide by the smallest number of moles. It's pretty close. This guy and this guy are the smallest, but it looks like oxygen beats everybody. So we're going to divide everybody by 3.4063, which is the smallest number of moles. And 3.4063. That's going to give us a 1 there and a 1 there. That will give us a 1.33 here. So this would be our empirical formula of CH 1.33 and O. I know you're hopefully screaming at the screen, that doesn't look right. And what doesn't look right is that's not a whole number. So remember that we do need whole numbers here. That is definitely not a whole number. And that is also one of those ones that are too far to round. So we do need to figure out a number to multiply that by to convert it into a whole number. So if we just simply look at 1.33 times 1, 1.33, 1.33 times 2, 2.66, 1.33 times 3, 3.99. That's pretty close to 4. So that is pretty close to round. So I'm going to want to multiply my empirical formula here by a factor of 3. Once again, it is not just multiplying this guy by 3, but we have to multiply everybody by 3. And if we do that, that will give us C3H4O3. And that would be our proper empirical formula. Once again, all whole numbers here. So this is one of those ones again where too far to round. Need to find that conversion factor or that factor to multiply everybody by. to get to a whole number. So once again, 3 steps here. Convert to grams, convert to moles, divide by the smallest. I guess that would be my 3rd step. And again, in this case, did not hit all whole numbers, so had to take that additional step to find that conversion factor. All right, let's take a look at a few more here to make sure. Why don't you try this one? Chemical analysis of a 1.078 sample of gas contains 0.54 grams of sulfur and 0.538 grams of oxygen. What's the empirical formula? So sulfur, a little 3207 action there on the periodic table, and oxygen, some 16 going on. All right, so take a few minutes here looking for the empirical formula. Let's see what you come up with. Okay, so let's take a look. We also want to do a similar thing here. We already have everybody in grams, so we do have 0.540 grams of sulfur. We do have 0.538 grams of oxygen. You may be saying, what do I do with this number? Well, this number represents the sample of the compound that is 1.078, and it should be made up of sulfur and oxygen only. I know it's made up of sulfur and oxygen only because if I take this number, which is how many grams of sulfur there is, and I take this number, which is how many grams of oxygen there is, and I add them together, it comes to this number. So that is just telling you that, yes, both sulfur and oxygen are the only compounds present here. Now, let's just say, for example, obviously this wouldn't be the case here, but let's say we had 0.540 grams of sulfur and only, say, 0.1 grams of oxygen. When I would add these two together, I got 0.640 grams of oxygen, or of the compound. That clearly doesn't equal our total mass. That means there has to be another element present. And I can find the mass of that other element by subtracting. In my made-up example here, again, nothing to do with this problem. But if I subtract this, that would give me the mass of like our unknown element. So sometimes it does happen that maybe, it'll tell you, hey, this is made up of sulfur, oxygen, nitrogen, for example. You can figure out sulfur and oxygen, add them together, subtract from the total mass of the sample, and you'd be able to figure out the mass of nitrogen in that made up example. But in this case, when we do add up the actual numbers given to us, it does equal that 1.078. And that means that we do know that that is the total 2 elements that are present in that compound, because they do add up to our total number there. So we don't have any percentages here. We're already in grams. So the next thing we want to do is take grams to moles. So we will use our periodic table and the molar mass to do that. Once again, we want grams on the bottom. So a little 3207 grams per mole for sulfur. And for oxygen, we got a 16 grams per mole. Grams again going to cancel here. And that will give us, in terms of our sulfur, 0.540 divided by 3207 gets us 0.0168. And we'll go one more, 38 moles of sulfur. We'll do 0.538 divided by 16. Going to get us a 0.0336. And we'll do a couple more here, 25 moles of oxygen. At this point, we once again now want to divide by the smallest number of moles. In this case, it does look like sulfur is the smallest number of moles. So we'll take 0.016838 and divide them both by that number. That's going to give us a 1 for the sulfur. We're going to divide this 0.016838. Going to give us, in this case, on my calculator, like a 1.99697. That is pretty close to 2, close enough to round. So this is a situation where it is definitely close enough to round. That means that we did hit all whole numbers. And that means our empirical formula will look something like this. 1 sulfur and 2 oxygens are sulfur dioxide. So here, okay to round because it essentially is that whole number of 2, basically. All right. Let's take a look at this one here. We got 49.3% carbon, 6.9% hydrogen, and 43.8% oxygen. What is the empirical formula? So take a few minutes. Let me give you some of these numbers. Probably remember them by now. We've been using the same elements. Carbon 12.01, still 1.008 for our friend hydrogen. And we can't forget about oxygen there, which is 16. All right, take a few moments here. Once again, empirical formula time. Come up with the proper empirical formula. All right, so let's see how you're doing. Once again, we have percentages. A quick look at our percentages and adding them together, we can check that it does add up to about 100%. That makes us know for sure we have all the elements that are present here. Again, if it doesn't add up to 100%, you may be missing an element somewhere along the way, and you probably have enough information to figure that out. Because it does add up to 100%, we could start by converting these percentages into grams by assuming 100 grams. That means that we will have, in this case, 49.3 grams of carbon. Remember, it keeps all the numbers the same. 6.9 grams of hydrogen and 43.8 grams of oxygen. Once again, we're going to use our periodic table and the molar masses here to convert these guys into moles, which is the next step that we want to do. So once again, we got them to grams. We went from now grams to moles. So using our molar mass, grams going on the bottom, 12.01 grams per mole of carbon, hydrogen, 1.008 grams per mole, and oxygen, 16 grams per mole here. Doing our division here, all the grams going to cancel, going to leave us with moles. So that's 49.3 divided by 12.01, looking like 4.10491 moles of carbon. Going to take it to a few digits here, not do a lot of rounding. 1.008 there, so 6.9 divided by 1.008, going to give us a 6.84524 moles of hydrogen. 43.8 divided by 16, 2.7375 moles of oxygen. So last thing we want to do here is divide by the smallest number of moles. All right, so in this case, it looks like we are going to be looking at oxygen as the smallest. So we're going to divide everybody by oxygen, which is our 2.7375. 2.7375, and a little 2.7375 action. That's going to give us a 1 there for our oxygen. For our hydrogen, this will give us about 2.5. And for our carbon here, that's going to get us a bunch of numbers in there, right? Looks like a 1.5 as well. Got like a 1.4995, which rounds to 1.5. So our empirical formula at this point, not looking so pretty. 1.5 for carbon, a little 2.5, and an oxygen. This clearly is not all whole numbers. This is a good sort of non-situation here. You could probably figure it out, 0.5. If we multiply everybody by 2, that is going to clear up our decimals. So if we do that, we get C3H5O2. A reminder, we need to multiply everybody by that as we get those numbers when we multiply everybody by 2. And this would now be our proper empirical formula, all whole numbers. In this case, the same factor will fix both of the numbers. And I would say that if you do run into this situation where you have multiples of non-whole numbers, probably the same common number there will fix the problem for everybody. In this case, as you can see here, it did. All right, good empirical formula action. So now that we talked about calculating the empirical formula, let's talk about what we need to calculate the molecular formula. So you really need three things to calculate the molecular formula. You need the actual empirical formula. So that is the first thing that you need. Now, you may just be given the empirical formula straight up, or you may have to calculate the empirical formula. So if you need to calculate the empirical formula, you'll follow those three steps we just talked about. Get everybody into grams, get everybody from grams to moles, and then divide by the smallest. Moles. Once you have the empirical formula, you then want to figure out the molar mass of the empirical formula. So you would then want the molar mass of the empirical formula. And the third thing that you really need, it's listed second here, but the third thing that you really need is the approximate molar mass of the compound you're looking for. The good news for this is usually in textbook problems, that's given to you in the actual problem. So usually somewhere in the problem, it will say something like the approximate molar mass of this compound is 180 grams per mole. It may say the apparent molar mass is 180 grams per mole or something like that. It may actually give you a range. So it may actually tell you, hey, the molar mass is somewhere between like 90 and 100 grams per mole. And that's okay. If it gives you a range, you could use either the low part of the range, you use the high part of the range, or you could use like the number in between the two, and you can use that as the molar mass. So what do you do with these numbers? Well, you take the estimated molar mass of the compound, which is what is given to you usually in the problem. You divide it by the empirical formula's molar mass, and you will get a number. And this number is usually a whole number. This is also a situation where, frankly, you could do a little bit more rounding if it's not a whole number, more than you would do in an empirical formula situation. So usually this number should be pretty close to a whole number. If it's not, it's probably okay to round in this particular case. What do you do with that number? So let's just say hypothetically we do this and we get a 4. And let's just say we had one of those earlier empirical formulas like A2B1. And this is my empirical formula. So you would then take this number that you got and basically multiply everybody in the empirical formula by it. And in my example, that would give me A8B4. And that will then turn your empirical formula into your molecular formula. So we get kind of a factor or a number to multiply the empirical formula by to calculate the molecular formula from it. So that's what we need here, those three things. Empirical formula either given to you or you need to calculate it like we've been doing, the molar mass of the empirical formula, and then the molar mass of the compound, which is typically given to you. So let's take a look at an example here. Empirical formula of acetic acid is CH2O. What is the molecular formula if the compound has a molar mass of approximately 60 grams? You know, it's basically the same as 60 grams per mole. All right, so the three things we need for molecular formula is we need the empirical formula, which in this particular case, they actually gave it to us. So we don't have to do any calculating. So that's good. We then need the molar mass of the compound, which is also given to us, which is our 60. And lastly, here we need the molar mass of our empirical formula. These are all kinds of abbreviations here, MMEF. So that we do have to calculate. So CH2O is our empirical formula. Carbon from the periodic table, again, is 12.01 grams per mole for the carbon. There are 2 hydrogens from the periodic table at 1.008 grams per mole. And 1 oxygen at 16 grams per mole. This is going to give us our empirical formula's molar mass of 12.01 plus 2 times 1.008 plus 16. It gives us a 3003, we'll call it. And that's our empirical formulas, again, molar mass. Now that we have our empirical formula molar mass, we have the molar mass of the compound. We're just going to divide the two. So we're going to take 60 grams per mole divided by 3003 grams per mole. And we'll take 60 divided by 3003. It's going to give us 1.998. Once again, that is fairly close, and it's pretty much okay in this case to round for this guy. That's going to be a 2. So what we do is we take the 2, and we're going to multiply the entire empirical formula by it. And this will give us C2H4O2 as our molecular formula. Now, sometimes people will write it like this, CH2O, and on the bottom right, put the 2. Personally, I'm more of a fan of distributing that 2 in there and writing your molecular formula like this. But in books, you will sometimes see people write it like that. But most of the time, it's probably a good idea just to multiply the number there and get the molecular formula like this. But if you do see it like that, that is sometimes how it is written. All right, so let's take a look at another one here. A compound has a composition of 1.52 grams of nitrogen, 3.47 grams of oxygen. The molar mass of the compound is somewhere between 90 and 95 grams. Determine the molecular formula and the molecular mass of the compound to 4 significant figures. So why don't you give that a try here? Nitrogen 1401. Oxygen is 16. In this case, we are not given the empirical formula. So remember, you need the empirical formula to figure out the molecular formula. You need the molar mass of the compound. And you need the empirical formulas, molar mass. So you have none of these except for number 2, which is, in this case, a range of numbers. So take a few moments and see what you come up with on this particular. Okay, so we got a couple things going on here. We do, obviously, as I mentioned before, we got the molar mass of the compound. We actually have a range here, so somewhere between 90 grams per mole to 95 grams per mole. So that's one of the things we need. We do need the empirical formula. We're not given it. We are given the grams of each of the elements. So we could go right from grams to moles in this case. So 1.52 grams of nitrogen using the molar mass from the periodic table, 1401 grams per mole of nitrogen. We also have 3.47 grams of oxygen. And using the molar mass there from the periodic table, 16 grams per mole of oxygen. So that's going to convert our grams into moles. And that's going to give us, not that would clear my calculator, 1.52 divided by 14.01. Going to give us a 0.10849 moles of nitrogen. 3.47 divided by 16, going to give us 0.21688 moles of oxygen. Once again, here, after we convert to moles, we're going to divide by the smallest, which looks like nitrogen in this case, 0.10849, 0.10849. Can give us a 1 there. We're going to take that, 0.10849, going to give us again a 1.9999, pretty darn close to 2. That gives us an empirical formula in this case of NO2, which is our empirical formula. So now we have the second thing that we need. Lastly, here we do need the molar mass of it. So calculating the molar mass of this guy, 1401 grams per mole for our nitrogen, plus 2 times 16 grams per mole for our oxygens. Going to get us a molar mass of 4601 for our empirical formula. Now it comes to the part where we need to figure out that conversion factor. Well, we have low end, we have high end, and if we go somewhere in the middle of those two, which you could add them together and divide by 2, we could use something like 92.5 grams per mole, which is sort of in the middle of these two. and divided by 46.01 grams per mole. That's going to give me 92.5 divided by 4601. That's going to give me basically a 2.01 as my factor. Let's say we'd use the lower end and we just use 90 grams per mole divided by 46.01. That will give us 90 divided by 4601. That gives us like a 1.96, which, pretty close to 2. Same thing here, pretty close to 2. And let's just say we ended up choosing the top end of our budget here at 95 grams per mole divided by 46.01. That's going to give us 95 divided by 46.01. That's about a 2.06, which is also about 2. So you don't need to do all three of these like I just did here. I just did this to demonstrate the fact that if you are given a range, and this sometimes happens when people are trying to figure out formulas, especially we use empirical formulas a lot in the laboratory because it's very simple to figure out an empirical formula. You basically could take a compound, say like silver, you do some reactions where maybe you put some chloride on it. And if you know how much silver you started with, you know how much silver chloride you ended with, you could subtract the two and figure out the mass of silver that you had, the mass of chloride that you ended up with, and you can figure out the empirical formula by following our steps. So sometimes you are given a range like this because they don't know exactly the number. And that's why when we get to this part here, a little bit more lenient on the rounding. But they all, in this case, basically equal 2. So no matter which one you choose, our molecular formula should be N2O4 in this case. And again, that is basically taking the 2 and timesing it by our empirical formula here. So if you do end up with a range, you could choose the high end, the low end. You could choose the number between the two, average it out, and it all should give you kind of the same factor there to figure out the molecular formula. All right, let's take a look at one more here. Phosphorus contains phosphorus oxide, which is phosphorus and oxygen together. It contains 43.64% phosphorus, 56.36% oxygen, has a molar mass of about 283.89 grams per mole. What is the empirical formula? I think on that last one, I forgot to do something, which was calculate the molecular mass of the compound. So before we do that, we will figure out the molar mass of this compound. That's going to be 2 times 1401 for our nitrogens, plus 4 times 16 for our oxygens. And if we do that there, before I move on to that other one there, since I forgot here, 4 times 16, that's going to be a 92.02 grams per mole. As you can see, the molar mass again in this compound is actually closer to that middle point that we chose. So kind of good we chose the middle point originally, but you could also see you will still get the same answer regardless of which part you chose there, lower end or higher end of the scale. All right, now back to this example here. So we're looking for the empirical and molecular formula here. Phosphorus 3097, oxygen 16. All right, so take a few moments and see what you come up with here. Okay, so let's take a look here. We're looking for both the empirical and molecular formula. It's probably a good place to start is the empirical formula. We have percentages of each of these elements. Again, just taking a quick look, got about 56 and 44%. So that's about 100%. That means that we do have pretty much all the elements present. So again, here we could start by assuming 100 grams. That's going to convert us into our grams, which will give us 43.64 grams of phosphorus. Also giving us 56.36 grams of oxygen in this case. Using the molar mass from the periodic table here, we're going to do a little converting to moles. So that's a 3097 grams per mole. And that's going to be a 16, looks like. Going to give us here 43.64 divided by 3097, 1.4091 moles of phosphorus. 56.36 divided by 16, going to give us 3.5225. We're at their point here in our empirical formula calculation to divide by the smallest. In this case, it does look like phosphorus at 1.4091. We're going to do a little dividing and give us a 1 there. And looks like for our second one there, it will give us like a 2.5, like 2.4998. Going to give us a 2.5. That's going to give us a molecular formula of PO2.5. I know what you're yelling at the screen. Not so good because not a whole number. So that's a 2.5. So that is something, if we multiply by 2, will turn into a 5. So we are going to multiply everybody by 2 here. That's going to give us a P2O5. And that's actually going to be our empirical formula in this case. That is the first thing that we need is the empirical formula to get to the molecular formula. We need the approximate molar mass of the compound, which was given to us here, so we're good. Lastly, here we need the molar mass of our empirical formula. So we can now calculate that since we have it. 2 times 3097 plus 5 times 16 here. Going to get us 2 times 3097 plus 5 times 16 and give us 141.9 grams per mole. Now we have all 3 of the things that we need. We're going to take the molecular formula's molar mass that was given to us of 283.89. We're going to divide it by the empirical formula's molar mass, 141.9 grams per mole. That's going to give us our factor that we need to multiply the empirical formula by. And that factor in this case looks like is going to be about a 2. By the way, it won't always be a 2. We hit a number of 2s in a row. So we're going to multiply this guy by 2, which gives us P4O10, which is our molecular formula in this particular case. So here we did have to calculate the empirical formula. First, get the molar mass of it, and then calculate the molecular formula. And we're able to figure out, obviously, our molecular formula from that. So this is probably the best way to approach it. There is an alternative way that, you can kind of figure out the molecular formula first and then the empirical formula. So since we have a little bit of time here, maybe I'll just show you that. I would probably recommend doing the separate problems this way first, and you probably won't run into any sort of situation, but just to show you maybe here. Let me see, maybe I got the next slide will work here. That's 43.64%. 43.64% phosphorus and 56.36% oxygen. 36% oxygen. 283.89. Okay, so if you happen to have a problem like this where you want to calculate both the molecular formula and the empirical formula, and you are given the percentages of each of these elements, and you have the molar mass of the compound, you could actually start with the molecular formula first by converting these guys into decimals. So you would divide each of these guys by 100%. And that would mean that basically there's 43% of this compound by mass is phosphorus. So if you take 0.4364%, which is our 43.64%, convert it to a decimal, and you times it by 283.89 grams per mole. That basically means that 0.4364 times 283.89. Out of that 283.89 grams, actually just leave it as grams if we want, 123.8895 grams of it is phosphorus. If you take 0.5636, which is our 56% converted into a decimal, and times it by 283.89 grams, which is the molar mass of the compound, we will end up with 5636 times 283.89 tells us that about 160 grams of this compound is made up of oxygen. So that's phosphorus and oxygen. So we kind of took the percentages, percent composition by mass, and the mass of the compound to figure out how many grams of each of those elements were present. At this point, you then can divide these grams of each of these elements by their molar mass from the periodic table. And when we do this here, we take our 123.8895 divided by 3097, and we hit a 4. And if we take 160 divided by 16, we hit a 10. And that is going to be our molecular formula in this case. And that is the same molecular formula that we just talked about. We get the molecular formula in this case because that is the molar mass of the molecular formula. So we're actually calculating the molecular formula first in this case. And we can then take the molecular formula, which is basically 4 phosphorus to 10 oxygen, which is basically a 4 to 10 relationship. And if we divide everybody by 2, that will give us a 2 to 5 relationship. That's the lowest we could go and still have whole numbers, which would then tell us that our empirical formula is P2O5. So in a situation, if you're calculating something like this, if you wanted to, and you have the percent composition by mass of the compound, and you know the molar mass of the compound, you could actually calculate the molecular formula first, and then just reduce it down to the empirical formula. So that's an alternative way, and I show you don't have to do it that way. I would highly recommend probably doing it this way. That is probably how your book does it as well. But this is, again, just another option as to how you could do that if you are, again, given the percentages of each of the elements present and the molar mass of the compound. And once again, we do start with the molecular formula here because we're doing it based off of the molecular formula's molar mass. So that's why we do start with the molecular formula first, and then we can reduce it down to the empirical formula. Once again, probably the better way, I won't say better way, but maybe less room for error is this way, and just do it this way, and you'll probably be in good shape. All right, if I'm not mistaken, dare I say, I believe that should wrap up. I'm going to say chapter 7 on this one. So part 2 of chapter 7 is in the books. Again, molecular formulas, empirical formulas, you need to know what they are. You need to know how to calculate both molecular formulas and empirical formulas from information given to you. All right, well, that sounds like a good one. Not too bad on this second half of chapter 7. So have a good day, and we'll see you, I guess, off to the next one. I'm going to go with chapter 8. It seems like what comes after chapter 7. Have a good one. Bye-bye.
We've come to the end of another lecture. It's always good to have some words of wisdom. What was that? Words of wisdom. Yes. Make like a proton. Stay positive.